Hi, everyone. My name is Shomo, and I just want to take a few minutes to walk all of you through some key concepts in distributed computing and fault tolerant computing. I will base this will be about a 20 or 30-minute short video and lecture on MapReduce. But really, I want to introduce some very key concepts in this video. Throughout this video, I will point to a number of papers. You can find all these papers in the description in the video, which on YouTube. And if you have any questions, I'll leave my email address. Please get back to me, and I will definitely get back to you with any queries that you have. I promise you that at the end of 20 minutes, you will have a different and unique perspective on fault tolerant distributed computing in the modern era. And I will briefly touch upon MapReduce and what that is. Before I tell you this entire story about MapReduce and fault tolerant computing, I want to give all of you some perspective and context. So it's the early 2000s. Internet companies are doing great business, and commodity computing and commodity hardware is slowly coming up. Hardware is getting cheap, and for the first time, we have web scale computing. So we have millions and millions of computers, millions of users connecting and consuming services. And companies like Google, for example, were faced with the unique challenge of big data for the first time. There was immense amounts of data that was being generated every single day, and they wanted to essentially run analytics and machine learning on that and find patterns in that. And even before any of the machine learning could be performed, they really had to gather all the data, that is, do data acquisition. Now, 15 years later or 20 years later, we take a lot of these things for granted. But in the early 2000s, these kinds of research problems were still being formulated, and people were still trying to find out how do you efficiently collect data over thousands of computers that is distributed? How do you do it in a fault tolerant way? And how do you do it fast? Companies like Google were generating a lot of data, and they essentially wanted to do lots of computations on it. This particular paper, MapReduce, was really built upon lots of different advances, but there are a few key concepts that I want to bring out. The first one is a reduced programming model. What that means is, at least as far as this particular problem was concerned, uh, these people at Google were not interested in solving any kind of problem or all kinds of computing problems. There were a few particular problems which were coming up repeatedly. One particular problem that we are facing is, given, for example, millions of documents, can you figure out what is the frequency of different words that appear in these documents? For example, I have a document that talks about, for example, cricket, another document that talks about baseball. There will be references to different players, there will be different terminologies. Can you figure out how many times, for example, the word uh, baseball or hit appears in millions and millions of documents? Can you figure out how many times the word Boston appears in all of these documents? How many times is Calcutta or Eden Gardens referred in all of these documents? Now, this is a very different kind of problem than saying, I want to figure out, I essentially want to run massively parallel cluster computing that is computing the state of the universe, for example, using computational fluid dynamics. That is not the problem that Google wanted to solve. They were very focused. They said that we don't want to solve the universe of all hard problems that exist and use commodity hardware to do that. That is a different problem, and people have done that. Google were really focused. They said that we acknowledge that this is a very hard problem. We're going to break it down into small little chunks. First of all, we're going to assume that all of these computers that have the data, some of them are going to go down. Hard disks are going to fail, networks are going to be slow, we're going to lose packets, so on and so forth. But can we still, for example, compute this sum? So again, the first important concept is a reduced programming model, and I'll break it down even further for all of you. Let me start by giving all of you a very simple example. Say you have 1,000 computers. Each of those computers stores a single number. And all I'm interested in is the sum of all these numbers. I am a server and all of these are clients. So we are in a client server sort of paradigm. There are thousands of computers which store, let's say each computer stores one number. And I tell all of these clients, hey, I want the sum of all these numbers. Can all of you send me send me those numbers? Now, this is an interesting problem because, as you will see, since I'm only interested in the sum, it doesn't matter in which order these computers send me their numbers. So if there are, say, three computers and they have the numbers 3, 7, and 10, the second computer could send me 7, then the third computer could send me 10. I know that now the sum is 17, and the first computer could send me 3. Now I know that the sum is 20. It doesn't matter in which order these computers respond and send me back those numbers, which means that it this is a reduced programming model. It means that there are no dependencies between any of these. For example, if I had matrix multiplication, for example, which really depends on the order. And if these three computers had three matrices which I wanted to multiply, then absolutely I needed one to respond first. And only once one is done, then I need to go on to two. Then I need to go on to the third computer. So there's a definite sort of order in which I want to expect results. This is not what this is. This is completely asynchronous. All of these computers can respond and as long as I get the numbers, I'm all good. Now, a very interesting thing also happens that if I have millions of numbers, and for example, I want to say the average, say for some reason 10 of those computers go down and they just don't send me the numbers, it's still all right. I mean, it's not the absolute best average that I will get, but the average won't be off by a huge amount because I have millions of numbers that I'm getting in. It really doesn't matter if 10 or 20 of these computers go down. So this is what I mean by a reduced programming model. I'm relaxing all my assumptions in my model. I'm saying that it's okay if some of these computers don't respond. It's okay if they respond in some weird arbitrary way. I don't really care because all I want is some metric which really doesn't depend on the ordering or doesn't depend on the way in which these computers respond, or it doesn't even matter if a small percentage of these computers don't even respond. So with this particular framework in mind, in 2004, some people at Google essentially built this system called MapReduce. And I will quickly share my screen and show you about this paper. And again, links to these papers will be available on the video below. And I will also send a repository which will have all these details. So please don't worry about it right now. You can look at this. You can look at this later. I'm just sharing my screen and showing you the title of this paper. It's called MapReduce, Simplified Data Processing on Large Clusters. And this paper starts out by talking about, again, what is the programming model, what they're really doing. The word essentially MapReduce essentially refers to a decades old strategy, which is called split, apply, combine. Say you have a large problem that you feel like is intractable. What you do is you split it up into small little pieces. Then you do your thing on them, that is, you apply. And then at the very end, you combine all of these things together and say that here is a result that I wanted in the very end. It's essentially split, apply, combine. So don't let all these all these concepts really sort of scare you. I mean, that's what it is. Map is essentially a function that comes from the functional programming world. Uh, if you don't know what that is, please don't worry about it. But essentially, what it does is, right as this signature says here, it takes, for example, one particular parameter and then maps it into a value. So it, for example, if I want to say I have a vector, it will operate on each of these. Uh, if I have an array, it will operate it will operate on each element of that array and then give me back something. And reduce is essentially just downstream of that and combining all of those values together. So if I go back and show you sort of a concrete example of this, for example, here is what the execution overview of MapReduce looks like. So there is one single program, uh, sort of a giant server program that says, "Hey, I want to count all the words and how many times they occur in 1 million documents." So it hands off into one kind of giant server program, which then starts lots of different client programs on thousands of millions of computers. Each of these workers will essentially be splitting up the task into small, manageable bites. They will take in all the input files. Then in the map phase, they will essentially figure out, for example, which word is in which file. They may create some intermediate files, for example. They will hand off their job to, in the reduce phase, they will hand off to other workers who will, for example, now sum up. So for example, and the word and is found in once in document one and twice in document two. In the reduce phase, this worker is going to output one, this is going to output two, and then they're going to combine all their results and say, okay, and is found 3 times in all these documents that I've seen. And then they're going to write to disk. All this really sits on top of a distributed file system because, again, you really need that. You need a file system which is essentially synced across thousands and millions of computers. Think of it as Dropbox that's running on millions of computers and you have millions of files. The discussion of a distributed file system is really subject for another lecture. But right now, assume that by some magic, whatever file that you have in any kind of disk is sort of transparently available to you. So it really, you don't need to really worry about on which computer it's really sitting on. It could be a computer in Sweden and I could be in India talking to that. It's as easy for me to access that as if it's right on my sort of hard drive. With the caveat that this particular system is really aware of locality, so it knows that, hey, if I have a file that's sitting closer to me, I probably want to get that instead of traveling 10,000 kilometers and creating some other computer, which is probably sitting really far away, and then there is network latency and all of that. But all of this is really sitting on top of a magical distributed file system. So you start off with a simple task, you break it up into little pieces. Each worker does its little bit. It then hands off into the reduce phase, which then computes, for example, sum or average or whatever, and then it outputs to disk. Now, I will get into the nitty gritties a little bit, but before that, I think I just want to, for example, highlight that in this particular setup, I mean, naturally, I've shown you 5 workers here. If there are millions of computers with their own hard disks, with their own network latency, some of them are going to go down. And what's going to happen over time is that some of these computers are not going to be able to respond. And say you expect this job to be done in 2 hours. But one of these computers has been working for, say, 90 minutes, and right at the very end, it just loses its hard disk, or it loses its network, or its system does a reboot, or some other unforeseen crash. Here is where I come to the second concept in this particular system, that it's fault tolerant. There was a lot of engineering that was done in to make sure that you could sort of recover from these failures. So naively, you could say that, like, I'm going to wait for all 1 million of these computers to respond. Otherwise, I'm just going to throw everything away and then start afresh. Now, if this was, yes, you, you could have done that, but 1 million computers is a lot. And with high probability, a few of those are definitely going to go down in, say, 2 or 3 hours or 1 day or whatever. And going back to that restricted programming model, you want to be sort of tolerant to these kinds of failures. So you could say that, yes, you could say that I'm going to wait for all of those, all or none. Or you could say, well, I probably don't care if a few of these go down, but I do care if that number is 10,000 or if it's 100,000 or whatever. So you could do two things. You could say that, okay, if it's 10 or 20 computers, then still please give me the result, because that is not going to be changed very, very differently, even if those 20 computers had given me those whatever numbers they had to give me. Or you could say that, well, I can see that this particular computer sitting in Sweden is probably taking a lot of time. Now, this is what the paper called a straggler. They're taking really long to show up. What I'm going to do is I'm going to anticipate that, with a million computers, probably there's going to be 100 stragglers, let's say. I'm going to start 100 extra jobs just to make sure that even if those computers do fail, I have enough redundant computations already set up. Now, how do I determine that number 100? That essentially, I mean, a lot of operating systems and distributed systems is very much an empirical science. So the authors in this paper did a lot of experiments over many, many months, and they just hit the sweet spot for whatever amount of data they were getting, whatever the network latency was. So essentially, it's sort of like a black art. But really, the concept is that the second big concept is that you want to start redundant computations. You know that a few of these computers are going to go down, or not going to respond, or are going to be stragglers. You want to be starting additional computers on additional nodes. With some probability, you might be wasting precious energy and precious resources, but with high probability, you're going to end up saving a lot of money and saving a lot of resources, because things do go down. Some of these computers are going to go down. There's going to be network latency. Hard disks are going to fail. So with high probability, you will actually end up gaining up by with these redundant computations, and over time you're going to gain back. You're going to actually recoup all these investments that you're making. So this is sort of the brief overview of all of these. There's a lots of implementation details in there. For example, if you go through the original paper, and I will have some tasks for you at the very end, just so that all of you can check your understanding and build on that, because I really want all of you to not really know all the nitty gritty details, but come away with some basic concepts of what's really happening with MapReduce. Was that those basic concepts are going to serve you well. For example, I mean, a lot of the optimizations that were done in this paper were about network latency. Suppose magically 50 years later, network latency is not the bottleneck, but computing is the bottleneck. How would you change your programming model? And say some other sort of constraints come up, and that's when all these concepts are going to be really, really important, because then you will be able to refer to these and say that, hey, it doesn't matter if these constraints have now changed. I just need to think about what is the right programming model and how do I ensure fault tolerance. So that's what I really want all of you to really, really get out of that. I'm going to step through this paper a little bit and sort of step you through some of the work in there. There's lots of stuff in here about data structures, fault tolerance. I already said that you really want to start off sort of processes early and have redundant processes that you're setting up. The paper, again, since it's really assuming that network bandwidth is a relatively scarce resource, it has lots of optimizations on locality, which means that that the network, that the entire system is aware that if a file is sitting close to you, you want to start a process, you want to fetch the file and do the process there instead of starting a process or fetching a file from Sweden or Australia or whatever. So it's locality aware. That was true 20 years back, probably still is true right now, may not be true in the future, but just something to keep in mind that these are the engineering decisions and engineering choices that they made. And uh, as long as you are crystal clear on what are the assumptions, then you can understand this really really well. It's a very very well written paper, actually. Again, I talked about backup tasks, how there's this concept of a straggler, that is a machine that takes an unusually long time to complete one or more of these tasks. And you really don't want to be waiting for that. So you want to be sort of proactive in starting off a few sort of additional sort of redundant processes. There's a lot of theory about sort of uh, combiners and all of that, which are additional bells and whistles have to be added on that. I won't get into these in this particular video, but please read the paper and you can get more information on that. My sort of my real objective in this video is to make sure that I communicate a few concepts very very well, and then point to point to some additional sort of exercises and sort of thought exercises that you can do, or even write up a few additional thoughts on what you would change. I'll come back to this in a minute. For example, there's lots of sort of performance metrics in here, and lots of references into all the kinds of experiments that they did. So this is telling you that this is very much an empirical science. Yes, there are strong concepts backing it up, but they had to do a lot of experimentation. So say 20 years later, some of these assumptions no longer hold. Uh, you can pretty much be guaranteed that you have to do a lot of experiments to figure out what each of these parameters are. For example, how many processes do you want to start? How long do you want to wait? And all of these are really questions that can be answered sort of empirically. There are theoretical guarantees that you can come, but still, uh, systems research is very much an empirical sort of hands-on, roll up your sleeves kind of research, which is really really exciting. There are references to, naturally, no system is sort of standalone. MapReduce was based on lots of very, very good research on distributed file systems, fault tolerant computing. I encourage you to read up some of these references, because these people do a fantastic job reviewing the literature. So please go through that. And I think that just summarizes this particular paper. If you have any particular questions, please email me. I will now do a brief segue. I'll just pause for a few seconds and let all of you think about, for example, say this is the year 2050, and say you have a new perspective on how to do fault tolerant computing. What would you change about this paper? Think critically about, say, for example, I take away this network latency issue, and you don't need to think about locality anymore. How would you change MapReduce? You still have commodity hardware, so hardware is still very cheap, but now it really doesn't matter if, say, a computer is sitting right next to me, or it's in Sweden, or it's in Australia, or it's in Brazil. Say network latency is no longer the bottleneck. Computing is still the bottleneck, but no longer network latency. What would you change about MapReduce? That's the first question that I want you to uh, leave you with. Please think about it for a few seconds. You can pause the video and think about it for a few seconds. And I will also pause here for a few seconds and get some water. The second thing I want you to think about is, can you think about some other systems that also do fault tolerant distributed computing? And please do not be, if you're a student, if you're starting out, please do not be intimidated by the fact that you haven't done any research. How can you sort of improve upon MapReduce? Just keep an open mind. I asked this question because many years back, when I was studying this paper as a graduate student for the first time, one of my colleagues and I wrote a term paper, which then became a paper that was accepted at a conference. Uh, we were actually biologists or computational biologists, and we were studying complex systems like the immune system. And what we were really doing is saying that we were studying, for example, ant colonies or immune systems. So, for example, in an ant colony, there's a nest somewhere here, and ants are trying to forage for food and then bring it back to the nest. And then in between there, they're communicating with each other. Some ants are going to get lost. Some ants are not going to find the food that they want. Some ants are going to find the food. As a colony, you can think about that you're really doing distributed fault tolerant computing because you still want to bring in the food. Say you send out 1,000 ants in the morning and 10 of them don't come back. You still want to have enough seeds in your colony by the end of the day. How do you ensure that? Say you are an immune system, say these are all cells in the immune system, and here is a virus. You're trying to find the virus. Say some of the immune system cells get lost and they can't find the virus, but a few of them do. And you want to build, for example, a biological system that is robust. And here is concept number three for all of you, that biological systems are very, very robust. They have been fine-tuned over millions of years of natural selection. And biological systems actually do robust, fault tolerant distributed computing. And here's a second question. Can you now take inspiration from complex systems like the immune system and ant colonies, for example, and propose to build a new kind of MapReduce system? My my colleague and I sort of we were graduate students when we first read the MapReduce paper. We had been studying complex systems for a few years back then. And as soon as we read the MapReduce paper, we thought that this is quite similar to how, for example, immune system cells are trying to find a pathogen, for example, or something else. And we essentially wrote a, a paper about how you want to, if you how you can build multi-agent systems for load balancing and distributed computing. I'll leave the link to the paper in the video. Please do take a read. And for example, here are, for example, instead of immune system cells, these could be computers that are connected to each other. And if you can form a cluster, for example, then you can do sort of computation much faster. And then you can dissolve these clusters once the job is done. And then it just frees up computing so that compute nodes can come to programs instead of programs coming to computers. So it was sort of dynamically allocating clusters and figuring out how many clusters or how many nodes are required to do a task. It just then forms a cluster. For example, here's a cluster of a few computers which are doing a job. Once they are done, then it just breaks up that cluster and say, hey, my job is done now. These computers can find more jobs. So it's sort of like immune systems cells that are trying to find pathogens, and that's essentially what we proposed. So I want to leave you with a few thoughts and a few exercises. Please write a few lines, write down your thoughts about what would you change about MapReduce. For example, if I relaxed one of these constraints, for example, network bandwidth is no longer a bottleneck. And then can you take inspiration from other systems that you have studied? For example, it doesn't even have to be a biological system. If you are in finance or if you are in banking or any other domain in supply chains, can you think about what you are studying, learn something from that system, and apply it to distributed systems? For example, I mean, how would you solve this problem if these are networks that are connected in a tree? So not just random nodes that are scattered all over the world, but now these are networks of computers that are in, for example, in some kind of social network. And there is some kind of distribution or something like that. So if there's a power law distribution or connectivity, how would you actually assign resources to these computers and how would you do that? So I really want you to get a few concepts from this paper rather than just sort of memorize the details. And because what's really going to really help you is these concepts, because all the constraints and all the technological hurdles are really going to change all the time. It's a moving target. But if you have crystal clear concepts, then you can apply them to whatever task is at hand. So just to summarize, there are, as I said, I wanted to give all of you a very unique perspective on distributed computing. It really is not only the province of computer science. Distributed fault tolerant computing exists all around us. Our immune systems do it, ant colonies do it, and we do it as human beings. Uh, One particular concept that I really want to drill again is a restricted programming model. Whenever you're faced with a task, you don't want to solve the hardest task that's really available. You want to break it down into a small chunk. You want to do a reduced programming model, just like Google did, for example. For example, you just want to compute the sum. You don't need to do anything fancy for that. So that's my first concept of a reduced programming model. And the second is fault tolerant computing. That is, if some of these nodes are going to go down, I really want to eagerly start sort of additional processes, just anticipating that some of these are going to go down. And initially, in a few of these cases, you might find that you lose time or you end up spending more energy, but then over time, you're going to gain a lot of efficiency with that. And then please have a thought about how would you actually extend MapReduce based on whatever system that you are studying. For example, if you're studying social networks or finance, please have a think about that, and then you can come up with your own sort of instincts and insights into that. And if you feel ambitious, you can write even a one-page summary of what you found and how would you actually improve MapReduce. And please email it to me. I would be happy to have a read and talk about it more. So I hope that this particular video was helpful, and then I have been able to give you a unique perspective on fault tolerant distributed computing, and I have been able to explain some of the concepts behind MapReduce. I hope that that was very helpful, and I wish all of you the very best in whatever endeavors that you are going for. Thank you so much.